if any or both of A, B be null sets, then we are not getting any order pair, therefore no question of getting relation. You see, order pair AA, members are 1, 2, 3, therefore order pairs will be 1, 1 for 1, 2, 2 for 2 and 3, 3 for 3. Good afternoon, welcome to btosacademy, welcome to my maths class. Today I am going to start the chapter relation and function. Already I have mentioned that the syllabus of 11-12 has been divided into two parts, such that few chapters have been divided so that initial part is given in the class 11 part and the detailed part is given in the class 12. Now relation function is a such chapter. Already students who are reading now in class 12, they got relation function in class 11. Actually, definition of relation, then relevant terms, domain, range, codomain, etc. were discussed in class 11. Now, detailed of relation and function both. I start relation first. First, we have to recapitulate. That is why I start like this. Relation. Let A and B both are non-empty sets. Then a relation is defined as the subset of A cross B. A relation R is a subset of A cross B according to given condition or restriction or property or law. Now, in symbol, R is subset of A cross B. Then we defined domain and range and codomain. Domain of R is set of A such that AB belongs to the relation R, and range of R is set of B such that order pair AB member of R, and codomain is the set B. I suggest students who have not learned relation function in class 11, they can recapitulate or revise. Next, we have two or three varieties of relation in class 11. One is null relation. Number 2, universal relation. Number 3, inverse relation. These are essential. Actually, on the basis of this idea, we shall now define relation on a set or relation in a set. Now, let me clarify. Non-relation, that means relation from set A to set B of order pair which will not satisfy the given condition or given restriction. We won't get any order pair A, B, where A is coming from set A and B is coming from set B, which will not satisfy the given restriction. And universal relation is the relation having all possible order pair AB, where A is member of set A and B, that means small b. When I am saying A, first A is small, actually this one. Where A member of set A, B member of set B. In case of universal relation, all possible order pairs AB will be the member of universal relation, and inverse relation of R is denoted by R. Symbol of inverse relation is this one. You have to pronounce R inverse. Now I take a simple example to clarify these three. A is a set having members 2, 3, 4. B is a member having members 4, 6, 8, 10. Now relation having order pair AB such that A plus B less than 6. Number 2, first I write down the conditions. say I take less than 8. After taking the two sets AB, I first determine relation 1 so that A plus B less than 6. R1 is equal to set of ordered pairs AB such that A plus B less than 6. Now let us think. List value or list member of A is 2 and list value of B is 4. Therefore, sum of two list members is 6. Therefore, we can't have any ordered pair AB so that A plus B is less than 6. Therefore, this relation is a null relation. Here, explanation will be this. Here, sum of list members of A and B is 2 plus 4. Therefore, we won't get any order pair AB where A member of set A and B is member of set B. Therefore, R1 is equal to null relation. Students who are following my YouTube classes, before following this topic of relation and function for class 12, you first view that episode of relation and function discussed for class 11. Thus, we see this relation is null relation. Then we take number 2. Here we find sum of greatest members of those two sets A and B is 4 plus 10, that is 14. Here, sum of the greatest members of A and B is equal to 4 plus 10. Therefore, every order pair AB will satisfy the condition A plus B less than equal to 14. Therefore, relation R2 is A cross B. Follow this. We add the greatest members of these two sets and find 14. Therefore, sum of other members will be, of course, less than 14. Therefore, relation R2 will be A cross B, Cartesian product of the given sets A and B. Therefore, this is universal relation. Now, number 3. A plus B less than 8. Now let us first find the ordered pairs. First I take this list value of A 2, 4, 6, then 2, 6, result will be 8. Therefore, after that 3, 4, 7. No order pairs except these will satisfy this one. Therefore, in this case, relation 3 is equal to 2, 4, 3, 4. Let me verify. 2 plus 4, 6. Less than 8, okay. Then 2 plus 6 equal to 8. Then I take this one, 3, 4. This one will be the relation 3. Therefore, inverse relation will be just the components or elements of the order pairs are to be interchanged. That means 4, 2, 4, 3. Now, here we can find the domain range of this relation. Here, domain R3 is equal to set of the first components. That means then range set of the second components. That means 4, 4, that means singleton set 4. And already I have mentioned codomain in this case. This set B. I think you have got the basic idea of relation from set A to set B, where A, B both are non-null sets. Now, the thing, if any or both of A, B be null sets, then we are not getting any order pair, therefore no question of getting relation. Therefore, these are the basics of relation. In the class 12 part, we have relation on a set, relation on a set or relation in a set, relation on or in a set, a, of course, non-null set. That means a relation from set A to itself, that is called relation on a set or relation in a set. Now we shall read variety of relation on a set. One thing I forget to mention, relation from set A to set B. In that case, we use arrow diagram. If we define a relation from set A to set B, then it is represented by such diagram. Say if we consider the relation like this, say A, B are related, we connect A, B like this. A1, A2, A3, A4 are represented by dots also. B1, B2, B3, B4, B5 are represented by dots, and by the side A1, A2, A3, etc. are mentioned. B1, B2, B3, B4, etc. are mentioned. Then we show the relation in this way, and from the diagram it is clear that domain of this relation will be set of A1, A2, A3, A4, and range is set of B1, B2, B3, B4. In other notations, we write like this: B1 is equal to R A1. Also, by this symbol, these three represent same thing, and in case of say B3, also we can represent similar notations. Here B1 is called image of A1 according to the relation R. B3 is image of A2, and A1, A2, A3, etc. are called pre-images. Now, relation on a set. That means, if R be a relation, in set A, of course non-null set, then R is subset of A cross A as per the given association. If A and B both are members of the same set A, and AB order pair is a member of relation R, then A is related to B, or we write B equal to R A. Thus, this is the definition of relation on a set or in a set. Here, from the definition, it is clear that domain of relation R will be subset of set A. Range of relation R will also be subset of set A. Next, we are going to discuss different types of relation on set A. Now, variety of relations, types of relations on set A. Null relation, universal relation, identity relation, inverse relation, first I discuss these. Already in case of relation from set A to set B, I have discussed null relation. The sense of null relation on a set or in a set is same. That means no ordered pair AB will be found satisfying the given association. Then universal relation on set A, that will be equal to Cartesian product A cross A. Then identity relation, inverse relation. I take an example to discuss these two first. Let K is equal to set of 1, 2, 3. Let us form relation defined by number 1, A plus B less than 2, where now let us illustrate. List member of set A is 1. Therefore, if we consider A, B both 1, then sum will be 2. Therefore, here the relation will be null set, because sum of any other two will be greater than 2. Therefore, relation is null relation. Then we form another relation R2 given by A plus B greater than equal to 2. As sum of list members of A and A will be 2, therefore sum of A plus B, A and B will be 2 or more than 2. Therefore, in this case, R2 is the Cartesian product A cross A, which is universal relation. Now, these two relations, null relation and universal relations, are called extreme relations. Also, these are quite trivial, that is why these two relations are called trivial relations. Next, identity relation. Identity relation of on set A is denoted by the symbol IA, identity relation, and that relation is defined by that means set of ordered pairs having both components equal. In this case, This is the identity relation. You see, order pair AA, members are 1, 2, 3. Therefore, order pairs will be 1, 1 for 1, 2, 2 for 2, and 3, 3 for 3. This is the identity relation. Then we take another relation to find the inverse relation. First of all, I take the relation A plus B, sum of the components is 4, that will be equal to, we consider first 1, then we get the order pair 1, 3, then 3, 1, then 2, 2. You check. Sum of 1 and 3 is 4. Therefore, one order pair will be 1, 3. Then other will be 3, 1. Then 2 plus 2, 4. Therefore, this relation is this one. Therefore, its inverse relation will be, we have to interchange the components. That means 1, 3, 3, 1, 2, 2. In this case, interestingly, inverse of this relation is the relation itself. Thus, I have described these 4 types of relations. Then we have more varieties. Now, I am going to discuss more types of relations. Reflexive relation, symmetric relation, transitive relation, equivalence relation. Now I discuss one by one. First of all, reflexive relation. A relation R in set A, already I have mentioned, non-null set, is reflexive if any member is related to itself. A is related to itself. Then that relation is called reflexive relation. Now, for this set, we define reflexive relation. The relation R is equal to better I say A relation. A relation R. Is this relation reflexive? Answer is yes. Because we see one is related to itself, that means one order pair is there. Then 2 is related to itself, that means 2 order pair is there. Then 3 is related to itself, yes, order pair 3 is there. Therefore, this is reflexive relation. Now, this is to be noted that the order pair 1, 2 is also there. Just you see whether A holds. A is member of R for all A belongs to set A. Then that relation will be reflexive. Already I have discussed identity relation. Now you see there is a difference of reflexive relation and identity relation. In case of identity relation, only order pair A will be there, no other extra member. But in case of order pair A will be there, any other order pair may be there except A. If you get any other order pair, that is AB, then this relation is reflexive. Hence, we can conclude that identity relation is also reflexive. Identity relation is also reflexive, but the converse is not true. Not all reflexive relation is identity relation. Therefore, we can make this note: all identity relation is relation, I write every, is reflexive, but all reflexive relation are not identity relation. Thus, for the set A, I have taken a reflexive relation. You can make other reflexive relations also, keeping these 3 order pairs intact. Next, we have symmetric relation. a relation R on set A is called symmetric if A R B implies B R A. That is, we can write also AB member of relation R, then BA will be member of R. Now, I take an example for the set A. I have taken this relation having ordered pairs 1, 2, 2, 1, 1, 3, 3, 1, 1, 1, 2, 2. Now, let me clarify. Here, 1, 2 is member of R, then 2, 1 is also member of R, and 1, 3, 3, 1, 1, 3 member of R, then 3, 1 is also member of R. Therefore, as per definition of symmetric relation, R is symmetric relation. Now let me take another example. I have taken another relation R1. Now let me discuss whether it is reflexive symmetric, as 1, 1, 2, 2, 3, 3, all these three order pairs have equal components. That means 1, 1, 2, 2, 3, 3 present, therefore R1 is reflexive, no problem. R1 reflexive. Now, for symmetricity, we see 2, 3, 2, 3 member of R, 3, 2 member of R, and there is another member 1, 3, but one, 3 present in R, but 3, 1 does not present in R. 1, 3 is a member of R, but there is no 3, 1. 3, 1 is not a member of R1. Therefore, R1. Therefore, R1 is not symmetric. Now there is another relation which is called antisymmetric. Antisymmetric relation. Let me clarify that one. A relation on set A is antisymmetric if A R B, B R A, possible A equal to B. A is related to B and B is related to A, or AB order pair is there in R, BA order pair is also in R when A equal to B. Such type of relation is called antisymmetric relation. One example can be taken. Say S is a set and its power set is there. That means set of all subsets, then two subsets of S, then the relation, subset relation R S1 is related to S2, means S1 is subset to S2 and S2 related to S1. That means S2 is subset of S1. Now already we know if A and B be two subsets, two sets such that A is subset of B and B is subset of A, then A and B sets are equal. Therefore, we find this one. Now this implies S1 equal to S2. Therefore, this relation, subset relation, is antisymmetric relation. Transitive relation, a relation R on set A is said to be transitive if R is reflexive R is relation R is such that AB belongs to R, BC belongs to R implies AC belongs to R. AB is an order pair of the relation R. BC is also there in the relation R. Then AC is there in that relation. Then we say R is transitive relation. Let me take one example. For this set A, I define the relation like this. Follow this relation. 1, 2 is member of the relation R. Then 2, 3 is also there, and 1, 3 is also member of R. AB member of R, BC member of R, then AC is member of R. Therefore, R is a transitive relation. Thus, I have discussed up to this reflexive relation, symmetric relation, and transitive relation. Then we have the last one, equivalence relation. For that, a relation R is called equivalence relation if R is reflexive, symmetric, and transitive. Therefore, if the relation holds reflexivity, symmetricity, and transitivity, then that relation is called equivalence relation. Now I take an example. Let S be the set of all triangles in a plane and R be the relation in S given by or defined by R equal to set of order pairs of triangles delta 1, delta 2 such that these two triangles are congruent to each other. Now I am discussing whether it is equivalence. For that, we have to follow step by step. I suggest students write like this. First of all, reflexive. If delta 1 be a triangle in S, then delta 1 is reflexive. Why? Any triangle is congruent to itself, as any triangle is congruent to itself. Therefore, then symmetric, or you can write reflexivity, symmetricity. If delta 1 is congruent to delta 2, then we can say, on the contrary, delta 2 is congruent to delta 1. Therefore, delta 1, delta 2 belongs to R, implies delta 2, delta 1 belongs to R. Therefore, R is symmetric. Transitive or transitivity. If delta 1 congruent to delta 2, delta 2 congruent to delta 3. First triangle is congruent to second, second is congruent to third triangle. Therefore, first and third will be congruent. That means order pair delta 1, delta 2 belongs to R, delta 2, delta 3 belongs to R. Therefore, delta 1, delta 3 is member of R. Therefore, R is transitive. Therefore, we have verified or proved relation R defined on the set of all triangles lying on a plane are reflexive, symmetric, also transitive. Relation R is reflexive, symmetric and transitive. Therefore, as per definition of equivalence relation, R is reflexive, symmetric and transitive. Therefore, R is an equivalence relation.